In previous isomerism, like tautomerism, as I said that in one of the neat paper they have asked a question related with ethyl acetoacetate. What was the question, you know? Ethyl acetoacetate, whether it will show tautomerism? Yes, because it will attain equilibrium as CH2 double bond COH, ketone group, enol, double bond and all. Remaining functional group COO, C2H5, remaining will be same. They will attain equilibrium between ketone and enol. Do you know, children? Ethyl acetoacetate in ketonal form, carbonyl form is about 93%. 93%. The major product, if they are going to ask, we need to write with respect to what the ethyl acetoacetate in ketone form. Let us move to, this is all about the structural isomerism and their types. Now let us move to second main class of isomerism as stereoisomerism. Stereoisomerism. What the? Stereoisomerism. Molecules having same molecular formula. Same what? Molecular formula. But where there is a different arrangement of atoms. What? Arrangement of atoms in space will be different. Arrangement of atoms in space, or in other way we can say that orientation of molecule. Orientation of molecules in space will be different. What? In space will be different. Let us move to the stereoisomerism in detail. As I said earlier that there are two types of stereoisomerism. One will be geometrical isomerism. Geometrical isomerism. Two or more molecules having same molecular formula. But in this case we are going to discuss related with restricted rotation of carbon-carbon double bond. Restricted rotation of carbon-carbon double bond. Have you observed that when the carbon-carbon double bond is there, you cannot rotate. Rotation of carbon-carbon double bond is different. Okay. There are two important conditions of geometrical isomerism. First condition that molecule should contain carbon-carbon double bond. And the second condition that each doubly bonded carbon atom, each doubly bonded carbon atoms must be linked with different atoms or molecule. Different atoms or molecule. It means that when the same molecules are lying on the same side, they are called as isomer. If they lies on the opposite side, they are called as trans isomer. Answer one question to me. Whether we can say that geometrical isomerism is possible in cycloalkane? Yes. Geometrical isomerism is also possible in cycloalkane. Cycloalkanes. Geometrical isomerism is possible in cycloalkane. Because in case of alkene and cycloalkanes both are represented by same general formula as CnH3n. Because of that reason, alkene and cycloalkane are geometrical isomer to each other. Let us move to the example. Let us move to the examples. Like but2ene. But2ene. means what? Double bond is present between second and third carbon atom. Double bond is present between what? Second and third carbon atom. Between second and third there is a double bond. Then two atoms of the molecule linked to the carbon-carbon double bond. CH3, CH3. Hydrogen and hydrogen. If they are lying on the same side, they are called as what, tell me? Cis isomer. If they lies on the opposite side, CH3, H, CH3. They are called as trans isomer. Cis isomer. Many of the examples we can write, but one point you need to remember that whenever the carbon-carbon double bond is present between first and second carbon atom, for example, hex 1ene in one of the question paper. In one of the question paper, they have asked question, previous question paper, whether hex 1ene will show geometrical isomerism. Our answer should be no. It means that if they contain only hydrocarbon at the first carbon atom, which are bonded with two similar group. Let me repeat once again. There are two important conditions for geometrical isomerism. One condition that it must contain carbon-carbon double bond. Another point that the two bounded atoms, two doubly bonded carbon atoms should be different. Now the question, you may think that why we are writing all these? Because due to restricted rotation of carbon-carbon double bond. If two bonds are there, we cannot rotate. If we are going to rotate, they are going to break. That means that due to restricted rotation of carbon-carbon double bond. Let me repeat the sentence. Due to restricted rotation of carbon-carbon double bond, geometrical isomerism arises. Geometrical isomerism arises. Cis isomer and the trans isomer. Cis and trans isomer both are separated by either by distillation or by gas chromatography. Either by distillation or gas chromatography. Another point need to remember that cis isomers are less stable, trans isomers are more stable. Why you can think that? Why I am repeating this sentence that they are less stable, they are more stable? Because in case of cis isomer, steric hindrance takes place. Bulkier groups are present on the same side, the chances of getting hindered. Whereas here bulkier groups are present on the opposite side. Due to which we'll say that they are having very least dipole moment. Approximately 0. Least dipole moment. Another point that cis isomer and the trans isomer. For example, if I am going to take maleic acid and fumaric acid, this is also question from one of the competitive exam. They have asked question related with maleic acid and fumaric acid. What is maleic acid and what is fumaric acid? Both are showing geometrical isomerism. Okay? Let us write maleic acid and fumaric acid. C double bond C, H, COOH, COH. Cis isomer is maleic acid. It is a dioic acid where the double bond is present between second and third carbon atom. Same way, fumaric acid, it is a trans isomer. Fumaric acid. Cis and trans isomer. When they are present on the same site, by heating, the chances are there to eliminate water molecule. Water molecule. That's why we'll say that maleic acid is unstable and fumaric acid is stable. Stable because COH group is very far away from each other. Very far away from each other, less chances of hindrance. But here the major chances of hindrance, and we said even in many of the organic topic that less hindered will be more stable compound. That's why less hindered molecule will follow substitution, more hindered molecule will follow elimination. This is the key point to remember complete organic chemistry. The last bit of this class from isomerism is optical isomerism. Optical isomerism. Actually, optical isomerism we need to continue in what, tell me? Haloalkanes and haloarine. But as I have started related with isomerism, let me take the definition along with one of the examples. Optical isomerism. Optics, it is related with light. That means that two or more molecules having same molecular formula. What, tell me? Molecular formula is same. But rotation of plane polarized light is different. Rotation of plane polarized light, which is generally abbreviated as PPL, is different. What is plane polarized light? Monochromatic light means single color. Monochromatic light which propagate in single direction, which allows to propagate in single direction. They are called as plane polarized light. Do you know? First optical activity they have observed in glucose and camphor. First optical activity they have observed in glucose and camphor. Now let us move to, as we said, two conditions for geometrical isomerism. For optical isomerism also, two important conditions are there. What are those? That we will see one by one. Two conditions are there. First condition that molecule should contain chiral carbon atom. First I will complete two conditions. After that we will discuss one by one. Chiral carbon atom. And the second condition that no plane of symmetry. What? No plane of symmetry. Chiral carbon atom means the tetrahedral carbon atom which is surrounded by 4 different atoms or molecules. They are called as chiral. And the molecule containing chiral carbon atom are showing chirality. In other way we can say that optically active molecule should be chiral. Later that we'll see, stereoisomerism and all, that we'll see in the next this one. Second condition that no plane of symmetry. Whenever a molecule is cut into exactly two halves, either vertically or horizontally by an imaginary plane, the half of the molecule should not be same as other half. Means non-superimposable mirror images. What do I mean? Non-superimposable mirror images. Have you observed? The right hand is non-superimposable for left hand. Right hand gloves with left hand gloves, right socks with the left socks. They are non-superimposable. Another point we can say that we'll go to the molecule, we'll go to the chemistry examples. Let us take an example like lactic acid. Lactic acid. Okay children, we'll complete in 2-3 minutes related with this. Lactic acid. What is lactic acid? CH3. This is carbon atom. Okay. Here COOH, H and OH. All the different atoms or the molecules are linked to the tetrahedral carbon atom. That's why it is chiral carbon atom. Its mirror image. Its mirror image will be CH3. Okay. H, CCH3, COOH and OH. Both are non-superimposable mirror images to each other. If you will observe the 3D structures, when they are cut into exactly two halves, vertical or horizontal, they should be, what, tell me? Non-superimposable mirror images to each other. They are called as optical isomers. Actually, remaining examples of optical isomers we are going to discuss in haloalkane and haloarine, along with stereoisomers, mesomers, and why some of the isomers are optically active, some are optically inactive, even they contain chiral center. All this we will discuss in haloalkane and haloarine topic. Thank you.